This is the second part of our lecture on Module 1, and before we proceed with what we are going to discuss in this module, we are going to review some relevant um, concepts that we have learned in the previous discussion. So, we know previously about this Big Bang evolution through time, and the main thing that we've learned from that is na-realize na to na the elements did not simply arise after the Big Bang. The elements did not simply come into existence after the Big Bang. In fact, as we all know, it took several times. I mean, we're not even talking of human time scales here. We're talking of cosmic time scales. So it took considerable amount of time prior to the existence of the atoms that we call. Okay, so we see here in this illustration, as we have discussed in our class, that particularly we are concerned on the era of nucleosynthesis, which roughly happens 30 minutes after the bang or so is our current knowledge on this one. And then after that arises the era of nuclei. So we now have nuclei, meaning we don't have yet, or the electrons are not yet bound, or um, the electrons are not yet bound to the nucleus. So that's why we have nuclei. And after, as I've said in the class jokingly, that finally the electron got commitment with the nuclei, and so arise the era of atoms. So we now have atoms. But we also learned that the atoms that we are talking here, particularly on the very first few instant, are not the entire elements that we found in the periodic table, but we know that the very first element that we have is the element hydrogen, which we denote as H. And we also learned in our class about the proton-proton chain that happens in our sun, where we have, or we started from a hydrogen atom, I mean nuclei, since this is a nuclear fusion, so we're dealing with nuclei, not atoms. So we have a hydrogen or a proton, H11, and then we ended up with a nucleus of um, helium, which we note as He42. Okay, so more on this one, we will review this part here. So this lesson will be going to go beyond helium. So we're going to ask the question of where do we get the elements heavier than helium. Okay, so this was already explained in our lecture about the nuclear fusion, the power generating mechanism of the stars. So we started with, as a summary, I will not go over through all of this in detail since we have discussed this in classroom. The basic thing that we need to note here is that the proton-proton chain for the case of our sun happens at the core because it has an energy requirement set at 1.5 times 10 to the 7 Kelvin. That means that some of the proton or the hydrogen that is on the surface of the sun far from the nucleus is not converted into helium. So it's really confined to the nucleus, the proton-proton chain, or the conversion of proton or hydrogen ion to helium. Okay, so that's it. And why, you might be asking, why that does it happen only on the nucleus? It's because of the fact that we have already discussed that also about the repulsion of your positive, I mean your same charges. So if you have positive and positive charges, so the law of physics dictate that they will repel each other. Okay, now you will be asking, now how come that we started with two protons and then we fuse it? So normally, then the normal thing that would happen from this one under normal circumstances is this should repel, since we are dealing with two protons. So you have two protons, so this should repel from each other. But since we have a very high temperature here, so that means our protons are very energetic, so it was able to overcome the repulsion of the protons, and so we were able to fuse protons here in this case, but only at the expense of a very high temperature or a very high energy, since temperature and energy are related. Okay, so as I've said, I will not go through in detail. So all I'm going to tell you is the fundamental things about this one. So basically, this proton-proton chain that fuels our sun started with protons, of course, and then we ended up with helium nuclei and two protons. So basically, if we're going to summarize that one, if we are going to count how many protons did we use, so we require actually six protons. So I mark it with check. So we require six proton, or roughly that is just six of H11. So we already discussed that H11, or the nuclei of hydrogen, is actually proton. Okay, and then from the six protons that we have, that will undergo the process of nuclear fusion, so we arise with the two protons, and then of course our helium nuclei. We have helium nuclei He24, or our alpha particle. And since this is a chain of fusion reactions, so normally along with this reaction is it releases energy. So in the form of, we know, in the form of photons, gamma photons, and also in the form of neutrinos. Okay, so yeah, I think this is more on the proton-proton chain as a review. So nakita ninyo dari class, you have a isotope of hydrogen, or the hydrogen ion in this case, because these are isotopes, as you can see. They have the same atomic number but different number of protons, as you can see in the subscript. So we have 1 and 2, and then yeah, also for helium, so we have another isotopes that we are dealing with here. So as a review, the first fusion of your two protons result into a nuclei of deuterium. So that is a heavy element, heavy isotope of hydrogen. So, and along with that is the release of a beta decay, and this one is a electron neutrino. Okay, so since we are basically dealing with physical science, and this is really not uh, core course, so as to say, that means we just want to get the general idea of what happens without going so much with the detail. So I would not want to bore you with the detail, so I'm hoping you're not bored yet. But anyway, the idea here is that you have two protons, and you arise with a heavier um, isotope or nuclei of hydrogen, along with some energy release. Okay, so the key thing about nuclear fusion is that it releases energy up to some element, which you already know is, I'm referring to iron, right? And then along with this reaction is, as I've said in the class, if we start with A and then we ended up with B, so if we sum up all the mass of the particles involved in the nuclear fusion, its mass will be significantly greater compared to the mass of its product. So that means that if I have the first protons, mass of the first protons, and then the mass of the helium nuclei that I come up after the fusion, it has a mass difference. And this mass difference then is not lost in some form, but it's actually released in the form of radiation. Okay, in the form of radiation, and of course with these particles here. So that is where your rest mass energy equation comes in of mc squared. Okay, so I have discussed this already in the class. So this is a review, and then this energy release that is associated with the nuclear fusion that is happening in the case, if we localize it in the case of our star sun, um, this actually constitute or provides the shine or the luminescence that we receive from the sun, the energy, the solar energy that we receive from the sun. And in general for the stars, so this provides them with their energy that they release in the form of uh, starlight. Okay, so this is also part of the review on the previous class. So we know that iron is the bane of the stars. So basically, um, from hydrogen, helium up onto carbon, oxygen, nitrogen, so the stars are able to fuse that, but that depends on the mass, which we will discuss later also. But when the iron fusion starts now, there is something wrong going on with the stars in that case. So that means it will no longer give off energy. So the iron fusion will not give off energy, but actually take energy from the core. And so that we call it the bane of the stars, because that is the beginning um, of another catastrophic event in the case of very massive stars. Okay, so let us start our discussion with localizing first what happens in our solar system in terms of how, since our topic will be on uh, stellar evolution, so we'll try to put it in the context first of our local star. Here, I'm referring to the sun, our sun, our very own star, in the center of our solar system. So we start with the molecular cloud, or we call this as the stellar nursery. It's because basically this molecular cloud that you have here comprises of many or greater mass compared to the sun. So it's very, very massive. I'm not putting here the digits, but I could provide my reference on the Google Classroom when you are curious about how massive is it. The thing is, it's very, very massive compared to the sun, and then the gravity will try to pull it inward, so it will try to compress this very great mass, since we know that, so we have discussed in the class that the force of gravity is proportional to the mass, and so the force of gravity will try to compress this one towards the center. And what happens as this molecular cloud is compressed, as you can see the arrow going towards the center here, is that the core temperature will start to rise. Okay, as the temperatures start to rise, and so you have now this one. Originally, this molecular cloud, of course, is moving. So it's moving, and then as this as it is compressed by the force of gravity, which is denoted by these arrows. So ang iyang mahitabuan na class is musaka ang temperature sa imong core, meaning katong sa imong center nga part ba musaka to iyang temperature ana niya pali mag-init, mamuinit siya ang kini nga center. And ang mahitabo dayon ana, since from a very wide, as you can see here, you have a very large volume and very wide ang span sa imo ang molecular cloud, and then it is compressed by the force of gravity into a very small, not very small, but relatively small na volume, or as you can see ang span niya ba mas nimubo. So you could think of kana bitong skater that that skater that opens up its both hands and then try to spin. So what happens then if the same skater will try to put his or her hands on its side or along its chest? What happens is that the rotation will be more rapid. So this is basically in physics the conservation of angular momentum. So what happens in your molecular cloud as it is compressed by the gravity is that it spins rapidly, meaning its angular momentum, its angular momentum is conserved, and as a consequence its angular velocity increases. Okay, so please do not get lost with the technicality. The whole thing is that from a very large volume that it occupies, and it's being compressed by the force of gravity, and as a consequence the temperature in the core rises. what happens then is it occupies now a smaller volume. So you could think of it as the skater, iyahan ang gibutang iyahang kamot diri dool sa iyang chest. And the consequence of that in physics is mukusog yung rotation. Okay, so pagkusog sa yung rotation class, mauna siya nga ma-notice nimo na ma-develop na nimo imong protostar here, and then ang mag-form sab na siya disk sa iya. Bali ang katong remaining masses bitaw nga dili na concentrate sa iyang center or sa iyang core, ma-form to siya disk sa iya ang equatorial plate kumbaga. Ngano man na siya. This is because if you notice ka nang magsakay bitaw kag kuan, magsakay ka og merry-go-round. So kung magsakay kag merry-go-round, tapos although at first di pa siya magtuyok, tapos ni sakay ka. Pag sugod ang nagtuyok, bisan paggatindog ra ka adira class is you will feel mangita jud kog pamaagi nga mohawid ka og sample or katong sa kabayo mohawid ka kay ngano you will experience some force that tries to pull you away or to push you away from the circular track of the merry-go-round. So ingon ana sabang nahitabo ani diri sa imo ang mga imong masses na naka-concentrate near sa imo ang solar core kumbaga or sa imo ang protostar nga core. So since it's rapidly moving pareha nang sa merry-go-round pag tuyok ana niya class ikaw nga gatindog maka-feel kang mura ka gipush pagawas, so that is actually a fictitious force. So probably ma-discuss ninyo na in detail sa inyong mga physics paano umaabot. So mo na mahitabo, so mao nang mo flat out na siya class then maghimo na siya disk. So that is actually the same logic with ang shapes ni Earth is dili gud siya perfect nga sphere, kundi oblate siya nga spheroid in which ang iyaang kuan class kay along its equator kay na flatten siya ba. It's attributed also of its rotation on its axis. Di ba kabalo tagatuyok man ng Earth sa iyang axis, mao nang murag mo flat ang iyang diri nga part sa iyang equator. So mausab na nahitabo sa imong disk diri. So from this one maghimo siya og kanang this concentric na mga disk because of its rapid lagi na rotation. Okay, so later in our solar system as na-defined na siya, this remaining mga mass on the disk, gravity further acts on it. So mao nang nag-brought about imong planets. And then the protostar on the center gradually evolved to be the main sequence star that we currently have, which is our sun. Okay, so that is in the context of our solar system. Now let's try to generalize that in the case of um, stars. So allow me to turn this off. So in the case of stars, so this is a stellar evolution graph that we see. This is from NASA. So the same with the evolution of our sun or sun-like stars generally. So we start with the protostar. Okay, the protostar. So this protostar then is now referring to the giant molecular clouds in which the force of gravity acts now to compress it, and as a consequence the core of that molecular cloud's temperature increases. So this is a rough idea on stellar evolution. Well, for the with respect to this course, we will try to get the rough idea on each, but not really delve or like dive too much on the more technical details since it requires some higher knowledge on quantum mechanics and general physics. So we'll just get the rough idea that will serve our purpose of understanding how these things happen. Okay, now we have this diagram here. This is actually a very important diagram in astrophysics and in astronomy, and this is the Hertz-Sprung-Russell diagram. So this Hertz-Sprung-Russell diagram, as you can see here, is actually a diagram that gives us an idea on the temperature of a star and the luminosity of a star. So we'll discuss luminosity in detail later. So as you can see here, you have white dwarfs, the main sequence, the supergiant, the giant. So um, this tells us some important data. So if we are given this graph and then the stars are plot there, we could actually infer or conclude some characteristics of the stars as we can see here. For example, When you look into the Proxima Centauri and probably Betelgeuse, so it almost, roughly, it almost lie on the same on the same vertical line. So that means when we look at the temperature of this Proxima Centauri and the what's this and the Betelgeuse, so you see that they roughly have, or probably not the same, but although also low temperature because they lie here on the same vertical axis. But although they have the same temperature, makita na to class that they have unsa man, they have different na masses and sizes, because we know that this Betelgeuse is a supergiant, and then the Proxima Centauri is near this end of the main sequence na spectrum here. And in terms of luminosity, makita nimo class na si Betelgeuse, although the same, almost probably the same temperature, I don't have the data, but from the graph dool ra sila no sa imong vertical axis, so dool sila temperature, since ang imo ang vertical ani class kay kuan man ni siya, ang imong data ani diri ba of the effective temperature. So kini diri imong data sub diri is on luminosity. So meaning if I draw line from here, so mao ni sila ang mga parehag temperature. So mao nang may ana ta diri if we interpret this that the Proxima Centauri and the Betelgeuse has the same temperature, but they have different luminosity. So if you look into the luminosity, so although we will define technically luminosity here, so but for the sake of this discussion first, we will go first with the luminosity of our sun as 1. So that means this is our standard one. That means um, if we try to compare how luminous is Betelgeuse with the sun, this is actually 10 to the power of 4, meaning Betelgeuse is 10 to the 4 as luminous compared to the sun. So this is actually logarithmic scales, no, kay 10 powers man siya. So but pasabot nga kana si Betelgeuse, although makita nimo sa at night, no, naaman ni siya sa constellation Orion, makita nimo ni siya at night, dili siya ingon ana ka kuan, dili siya kay ingon ana ka tawag ani kay kasiga sa sun, di ba? So that is attributed also of its distance away from the earth. So although mas dako gyud kana siya compared sa sun, pero makita lang nimo na siya as a star nga gamay sa kanang sa Orion na constellation kay tungod sa iyang kalayo. But in terms of the luminosity, when you talk about luminosity, I think nakita siya diri, no? So luminosity is actually a function of the area and then some Stefan Boltzmann constant here. So again, do not get lost with the mathematics here. All we are going to do, as I've said, is to get the idea on how this happens and how this all relate or add up to the explanation. So t to the 4. So nakita ni mo class na the luminosity is a function of what? It's a function of area, and then it's also a function of temperature to the fourth power. So that means magbase ang luminosity sa isa ka stellar object or sa star in this case sa imoang temperature o sa imong area. Now, if you try, as I've said, lantawon nimo si Betelgeuse o si Proxima Centauri, so roughly they are of the same temperature kung lantawon nimo diri. But I know probably dili gyud na sila the same temperature, no? Naagi variance silang temperature, pero duol-duol sa makita nato sa graph. So kini ilang T, so duol-duol, so dili kani siya mo affect. Ang ilang area then will affect sa luminosity. So as you can see, ang luminosity ni Proxima Centauri is 10 to the negative 4 with respect to the sun, no? So yung nana dimmer siya kumpara sa sun. Ang imong Betelgeuse is 10 to the 4 ang iyang luminosity, 10 to the positive 4 compared to the sun. So ang atong logical inference from that is that if they have different luminosity, and since the luminosity of Proxima Centauri is low, meaning yung luminosity kay gamay, then since we already discredited the temperature, kay probably dool na, no, makita na to diri sa graph na dool ra siya, then it could be logical to say that ang iyang area karon ana nga star is smaller. So that means ang iyang radius gamay. So gamay ni siya nga star. Although the same silang temperature ani. So ang isa nimo kay si kana si Betelgeuse kay as we have said, almost atong disregard ang temperature kay makita nato na duol na sila no, roughly the same. Pero nakita nato that the luminosity is high, so that means or it tells us that this star probably is massive and it has a large area also. So dako siya. And that is true because Betelgeuse is a supergiant. Okay, so kana. When you talk also of the luminosity, so unsa man siya? Unsaan man nato ni siya pagkuan. Kining comparison nga naa nimo diri kining 1, 10, 10 to the 2, 10 to the 3 nga mga star, 10 to the 4 is if nga naa ni siya class, if nasa Earth, nata diri sa Earth tapos natay set distance kung kana si Sun nimo tapos og si Betelgeuse or unsa pa na ang mga stars dira og kini si Proxima Centauri. So akong kanon ha, kini Proxima Centauri tapos kini si Sun o kini si Betelgeuse. So the thing to make sense of kining luminosity niya diri class is that if they are located at the same distance from the Earth, which is not dili tinuod, di ba? Proxima Centauri mao yung pinakaduol na to no sa atong solar system. Then kining si Betelgeuse layo na gyud na siya. So which is not the case as I've said, pero para lang ma-make sense na to ning unsay pasabot sa luminosity ba, kung kana silang tulo ka object, butang na to na siya at the same distance from the Earth, buot pasabot is kana si Betelgeuse dapat 10 to the 4 times, so meaning 10 to the 4. So unsa man na siya, pila man na siya, that is 10, 1, 2, 3. That will be 10,000 times as bright as the sun. Kumbaga, kung the same distance sila. But we don't notice that in reality. That is because Betelgeuse is so far away from us. Mas duol gining sun na to. So mauna nga although it's very large, super giant, and although it has a high luminosity, atong makita siya sa during nighttime nga gamay gihapon gyud siya. Okay? Og buot pasabot ana as continuation is kining Proxima Centauri nimo kung pareha ni siya kadulon sa sun, then it will be 10 to the negative 4 or 10,000 times dimmer than the sun. Okay? But the interesting to note, as I've said, is although they have different luminosity, they have roughly the same nga temperature in the case of Betelgeuse and Proxima Centauri, or so according to the data. But we will try to check it in our class, kanang kuan gud class kana bitawng specific gud nila nga data para makahimo gyud tag kanang significant comparison, kay rough comparison naman atong gibuhat ani based on the graph. So kana lang iyang idea on how you say that this ang luminosity ni for example ni unsa pa may laing star diri, luminosity ni Deneb or ni Rigel kay at 10 to the 5 more than the sun. So mao ni pasabot kung imo na silang gipangbutang at the same distance from the sun, it would appear that they will be more luminous or masiga siya tag 10 to the 5 times compared to the sun. Okay? So the logical answer then nga nung wala na to na nakita nga murag na ay sun sa ato ang pagkagabi is that they are located very very far away from us. Okay? So kana siya. And kini pud dai siya class kining imong Hertz Sprung Russell diagram. This tells us so much and is very helpful in terms of explaining the stellar evolution. So gikan sa main sequence unsay mahitabo sa imong star. So mao na ang atong mga discussion sa sunod ani nga session. So for example, kini siya, this is a very good example no of kato kong giingon nga gikan sa unsay evolution kumbaga sa imo ang protostar tapos mahimo siya nga star na gyud kumbaga. So kani, okay, so if nakita nimo, this is really a function, giklaro gyud ani nga picture, giklaro gyud ani nga kuan class figure na the evolution of a stellar object or a star is very dependent gyud siya on its mass. So you see, giklaro niya nga dependent gyud sa mass. For example, if you started with a smaller mass, for example 0.5 lang siya sa mass sa sun, no? So ang iyang evolution ana niya kung mahimo na siyang main sequence nga star is kung lantawon mo iyang temperature, mubo sab na siya temperature class. kay magbo siya temperature. So madiscuss na to na in detail, and I think you can think naman of an explanation nganong ingunana, no? Pag more massive siya, makita nimo pag more massive mag-progress siya diri sa increasing temperature. So you start with 3,000, nakita nimo diri padulong ka sa 30,000 nga temperature. And this is in Kelvin, by the way, it's not in Celsius. So kana, so 15 solar masses, nakita mo na siya sa blue end here. So makita sa no 30,000 ang iyang temperature. Kung mahimo na gid siya, mahimo na gid siyang main sequence nga star. So sige lang, ma-discuss na to ng mga main sequence, mga inana later. So makita na to na if we relate it with our previous discussion bitaw about sa katong wavelength. So kabalutan na ang wavelength sa red kay unsa man, the wavelength of red is high and its frequency is low, and as a consequence iyang energy class is low. Ang wavelength sa atong violet or towards the blue end sa atong spectrum, if you remember, ang iyang wavelength ana is mubo, but its frequency is very high or large, and as a consequence its energy is high. So nakita nimo sab diri in terms of corresponding it with temperature, nakita nimo na the red end of this continuum here is katong colder. So kanang mga red na tong star, mga cold na sila, or dili cold in our kuana kanang human terms, pero on the stellar scale cold sila, meaning gamay sila temperature. And then kining imuhang mga blue end diri or mga blue stars nimo, mao ni siya ang imo ang stars nga hotter in terms of temperatures. So, yeah. So, we might be asking, unsa ang nag-keep sa integrity sa shape or volume or sa structure sa isa ka star? So, this is actually the balance of the gravitational force and the thermonuclear force. So, mao na nahitabo sa imong star. So, nganong makakip na siya sa iyang integrity sa iyang structure and shape, it's because naa na siya delicate balance class. The gravitational force is actually trying to compress your star. So it's trying to compress it. It's trying to push it towards the center, no, kanang imong gravitational force, and as a consequence it leads to the heating up sa imong core ana. Pero unsa may nahitabo, we don't really see nga automatically mo collapse gani siya, no, under the influence of gravity, because as your core is increasing in temperature, it's also, we have known, diba, it's fusing um, uh, lighter nuclei to heavier nuclei, and as a consequence natay thermonuclear force ana niya class, or kanang energy nimo nga release from the fusion dito sa core. So mao na siya ang mo stabilize sa compression nga gidulot ni gravity. So mao ni siya ang delicate balance sa imong star. But this balance will not always occur. In fact, along the evolution of a star na ay mga interplay along this balance, and kung mudako ang isa na ay consequence ana niya sa integrity sa structure sa imong star, even it dictates sa iyang life. So kana siya. So think of it as the balance of gravity trying to push it down, and the thermonuclear force trying to blast the surface of the star also. So mao na nahitabo na ay thermonuclear force na mura gusto bungkagon ang star. So ang integrity sa star, pero naapoy mo counteract ana niya because the star has a mass, na mo counteract niya nga gravitational force. Mao na nga magbalance ra na siya, so it keeps the integrity of a star as an entity. So for the cases of stars, not necessarily stars, no, for the cases of yeah, I think stars sa correct term. For the cases of kana bitawng imuhang kuan class, imuhang protostar nga ma-develop nga kuan siya less than 0.5 ang iyang mass sa sun. So ang iyang development ana is that of course from a protostar, kabalo man kita magsugod siya kuano katong molecular cloud or nebula or stellar nebula, so or giant molecular cloud, whichever is ano. So from the references, the references either call it stellar nebula, a nebula, or a giant molecular cloud. So from that, kung ang imong mass again is small, or that means 0.5 of the mass of the sun, so this is a low mass star, imong development is you go with the protostar nga phase, and then you will be on the main sequence. So kung lantaw nimo na sa kuan class diri, sa imong Hertz-Sprung-Russell diagram. So kung gamay ang imong massa star, moadto din na siya sa main sequence. Kung naa na siya sa main sequence nga ni MS, this is now the phase when it's actually burning hydrogen or fusing hydrogen na siya. Mao na tawagon na nato siya as main sequence. So from a protostar, once it starts fusing hydrogen, so tawagon na nato na siya as a main sequence nga star. So as I have said earlier, lantaw na to makita na to na this is really a function of mass, no? Ang iyang kapadulungan niya ba nga star o iyang temperature nga iyang i-end up. So mas ma-appreciate na to na sa preceding slides here or preceding slides. So okay, so nana siya sa main sequence star and you can see low mass, so na siya sa red. So ang iyang temperature ani class ubos-ubos gid siya on the stellar scale pod no. Ubos-ubos siya. And then along its development, so moabot siya sa white dwarf. Mahimo siya nga white dwarf. So kining white dwarf, so makita sab nato no ang white dwarf kung itong lantawon diri sa imo ang kuan, Hertzsprung-Russell diagram is that although gagmay sila, kaya nga white dwarfs no, but this is not, again ako emphasize, gagmay nga sa earth nga things, pero stellar gani siya nga kagagmay. Although gagmay na siya class, but they are actually very hot. So dagko silag temperature na siya diri. So this area here, as you can see, towards the left end kay mag-increase na yung temperature. So naay mong mga white dwarfs diri. So they are of small nga sizes because makita sab nimo no kay ang luminosity gamay man sab. So meaning faint na sila lantawon. So faint na ni sila but their temperature is actually very high. Ngano man, if you try to think of its kuan class, of its size, so that means na-reduce siya for very very small nga ano, due to gravitational influence, na-reduce siya og small nga tawag ani small nga volume. So that means na ano yun siya kanang as a consequence ba kabalo ka nga kung ma-compress nimo na siya by the force of gravity mag-increase ang temperature. Pero ang nahitabo sa white dwarf karon is ang nag-keep sa integrity sa white dwarf is natay ginatawag na electron degeneracy pressure. So, we will not discuss in detail but just for you to know na ang nag-keep ani niya class nga dili siya ma-further pabitaw og kanang dissociate or ma-further squeeze sa force of gravity kay na siya electron degeneracy pressure nga ginatawag niya. So, it's highly technical term. So, kana siya sa quantum mechanics na ni siya pero at least we know nga nganong maka-maintain siya sa iyang integrity as an object. It's because of this electron degeneracy pressure. And kinahanglan ang requirement ana niya class is 1.4 gud dapat yang mass sa imong white dwarf, SM solar mass. So this is what we call the Chandrasekhar limit. Chandrak I'm hoping I spelled it right. Sekhar limit. So mao na siya ang iyahang pinakagamay nga allowed mass ani imong white dwarf. Otherwise, makita na to sa mahitabo. Okay? So, kana. So, this is for masses nga less than 0.5 mass of the sun sa ato ang star. So, this is an example of a white dwarf that is imaged by the Hubble telescope. So, can you know? Okay, so they are cool white dwarfs in the star cluster M4. So you can estimate the age of this white dwarf based on some models and it's found to be 12 to 13 billion years old, which is consistent with the age of universe no kay if you find this to be kuan butang talag 15 billion years old, so meaning ni kuan pa siya, ni lapas siya sa age sa universe, then there must be something wrong in either of the models kay nganong nilapas man siya, so that means gauna palagwar siya sa Big Bang. So kana, so this is a good thing that this fits our kuan the current estimate of the age of the universe. So at least kabalutan ang atong models are in kuan ba in agreement. So kana siya in M4. So another thing is when we deal with stars class na 0.5 man to no, 0.5 ang iyang mass karon is kung naanata sa medium mass para sa atong sun, so 0.5 to 8 times the mass of the sun ang iyang development ana is magsugod siya of course as nebula and then a protostar, tapos main sequence siya nga star. So makita nimo kung sa kato bitang masses below 0.5, red to siya diri nga star. So pag abot sa main sequence aning 0.5 to 8 times the mass of the sun, so it lingers around the yellow. And so is makita na to nga yellow atong sun. So yellow, kuan man na siya kanang medium mass man na siya nga star. So yellow. And after that is mahitabuan ni kung ma-recall niyo atong discussion sa proton-proton chain bitaw katong sa nucleus, diba taas mo kay temperature ani. So it will again diri ra sa nucleus nga part or sa core niya nga part class mag-fuse ang imong hydrogen or imong proton. Okay, mag-fuse imong proton, so that means mo unsa may mahitabuan ni pag mag-fuse ni siya, naagyud ka understandably nagyapon ni siya diri nga shell kana sa outer nga part ba nagyapon kay hydrogen ani. So as this hydrogen are fused, sa imong core na lang will be populated with helium, di ba? Mahimo ng helium. Mao man ay itong basic nga proton-proton chain natay hydrogen nuclei makahimo tag helium nuclei. So dito sa imong core, kung helium nuclei na to siya or kung ma-exhaust na nimo, so kining imong proton mahurot na ni siya dito sa imong core. So meaning all of the protons now is converted into helium. Ang mahitabo ni mo na class, although depende yun siya sa mass niya, no? Ang mahitabo na niya karon is that mag-stop ang imong fusion diri kay nahimo namang helium ang tanan. So ang helium, para ma-fuse ang helium, mag-require na po niya siya taas nga temperature, meaning kinahanglan taas na po nga temperature para maka-fuse ang helium. But at this time ang imong nucleus diri or imong core sa imong star kay kuan pa man ang iyang temperature nga naa kay kato pa man maka-fuse og hydrogen, tapos wala pa siya ni saka ba dahil na helium na ang imong mga hydrogen dito. But of course, as I've said, sa imong outer surface naagid gyapon ang helium pero wala na fuse ang hydrogen kay dili man nakaabot ang temperature aning sa imong surface class. Dito ra man gyud siya sa iyang core ang nakaabot og temperature na ma-fuse niyang ang hydrogen to helium. So mahitabuan na karon is since ma-shutdown man ni diri, so meaning ang iyang radiation bitaw na nag-keep niya katong giingon bitaw nako iyang thermonuclear force na nag-blast kumbaga murag mo try to bungkag sa imong star ba, mag-blast sa iyang surface is now shut off. So meaning mo shut off ni siya. So ang influence sa gravity will be pronounced. So meaning mas kusog na dayon or mas makita na to ang influence sa gravity kay kini nawala man eh. Kining force na pagawas outward, kining thermonuclear force. So that means that it will try to compress. So no, the force of gravity will compress your star in this case. So pag compress ana niya class, ang iyang kuan na niya, of course kung mo compress siya, imong volume ma-decrease sabi imong volume, di ba? Pero ang consequence nimo is mas ma-dense na imong core, and pag i-compress mo na ang core nimo ana karon will increase in temperature, meaning the temperature in the core will drastically increase. Okay, mo kinahanglan siya increase. Pero in this increase, magsaka man ng temperature sa imong core. So napo na siya effect sa imong surface nga temperature sa imong star diri. Pero pag saka while the temperature is increasing dito sa imong core, tapos wala pa gyapon niabot sa energy nga required or temperature nga required ma-fuse niya ang helium. So wala pa siya kaabot ana. Pero pag increase na sa iyong temperature, ang katong mga hydrogen nga nasa iyong surface karon, magsugod na pa to sila fuse. So mao na siyang isa ka reason nga nung magkaroon na ng swelling na dayon na imong star. So kaning mga hydrogen nimo diri mag-fuse ni siya. So magkuha na po ni siya. Akong himuan siya concentric circle ha para mas ma-appreciate ninyo ang kuan bitaw, ang concept. So there is a core na himo na ning helium, di ba? Proton-proton chain ana tay mga helium nuclei ani. Pero as I've said, ang imong hydrogen nag-reside gyapon na siya sa surface. So ako nang gibalik unsay nahitabo, ang force of gravity tries to compress that, and as a consequence mo increase ang temperature. Pero ang temperature nga requirement para ma-fuse ning helium into heavier nuclei kay wala pa na-achieve. Pero as a consequence, of course, ang imuhang temperature aning sa imong shells diri nga naay hydrogen class kay ni-increase na siya sufficiently such that maka-fuse na pud niya ang hydrogen nga naa diri. So i-fuse niya ang hydrogen to helium na pud diri. Okay, so manay mahitabo, mag-fuse ni siya diri to helium. So naa na pud kay thermonuclear force na mo blast sa iyang surface. So this will lead now nga unsa man mo contribute na pud ni siya sa kuan kanang thermonuclear outward force nga somewhat mo counter sa force of gravity. Pero this is very ano paghihapon. Magpadayon paghihapon ning kuan niya class, iyang compression kay iyang core diri gyud sa iya mismo sa tunga-tunga ba wala man siya thermonuclear force nga mo support ana niya. So ang influence sa gravity pronounced gyapon kaayo at bisan pag nisaka na ang temperature nga ma-fuse ang hydrogen sa iyang surface. Pero ang helium wala pa man such that nga mo saka nagitaas na gyud kay temperature niya class, meaning the temperature is so high, ang mahitaboan na nimo kay ang imong helium karon nga nuclei sa iyang core will now be sa man ma-fuse na po na siya. So ma-fuse na siya into heavier element which ako lang ibutang as blank para makita na to na sa kuan sunod sa mahitabo no. So kanang helium niya ma-fuse na into some unknown element, although kabalo ta ani nga unsa ni nga element ato lang siyang ipatrill to some unknown element, and when that is fused, so since this is nuclear fusion mag-release na siya energy, so mauna siya nga mag-blast na pud ning kuan diri katong imong thermonuclear force. So nag-on na pud kumbaga imong engine diri sa core sa atong sun fusing helium to some element. So mao na siya karon moabot na din siya sa iyang red giant nga phase. Kay mo balik na mo pud siya swell kay mo kusog na mo pud to iyang thermonuclear force nga ma-encounter na pud ang gravity ba, so mao nang moabot na siya sa iyang red giant nga phase. And then pagkahuman ani niya is di ba naman tay ginaingon nga Chandrasekhar limit, ang sunod gyud ani sa mga medium mass stars class kay padulong gyud ni sila sa white dwarf. So mao gyud ang end, mahimo ra pud siyang white dwarf. So meaning gamay from giant mahimo na siyang small nga star pero init kayo. Init kayo pero in the case of medium mass manggod, kining imuhang low mass stars walay problema no sa ilang death kay padulong sila white dwarf. Dayon mo fit in pod sila sa 1.4 solar mass which is the CL or the Chandrasekhar limit. Pero kining imong mga medium mass stars along its evolution pag abot niya red giant is they need to blast off ang uban nilang solar material bitaw nila or ang ilang stellar material nga nasa ilang surface class kinahanglan nila na i-blast off such that ang remaining yun nga mas sa core sa star will be 1.4 solar mass gyapon. Kay mao man ni atong requirement Chandrasekhar limit. So kanang 1.4 solar mass, so mao nang natay planetary nebulae or nebulas kay kuha na siya. They are basically the remains of a dying star nga lapas siya 1.4 solar mass ang iyang murag bitaw core niya. Kay kinahanglan man gyud ta mo follow sa 1.4 solar mass because this is a physical law gyud siya class governed by quantum mechanics. So kinahanglan man 1.4 mao nang iyang i-blast off na iyang remaining masses niya diri. So mao na planetary nebula then karon, and then since it's emitting radiation no ang imong star diri, so mao na siya nga mag-glow dahil ning imuhang mga kuan diri, mga elements kumbaga nga gikan sa imong original nga star nga gi-blast off niya just for it to settle down with 1.4 solar mass. And so, nanan kay white dwarf dayon. So this is an example of a planetary nebula, the Cat's Eye Nebula. This is a nebula in the constellation Draco. So kini, so maoning nakita nimo sa tunga, this is your white dwarf and maoni siya ang iyang give off or iyang gi-blast nga solar mass ay iyang stellar mass just for this white dwarf to follow or to be consistent with the 1.4 solar mass set by the Chandrasekhar limit as a consequence of some physical law, no? So kana siya. That was the case for the medium mass stars such as our sun. So our sun will follow this tawag ani kanang will follow this process in its evolution. So one thing to note also is that the the creation of this planetary nebulae, as you can see, or a planetary nebula, is different from what you called as the what do we call this supernovae. So this is not the same with supernovae. So supernovae actually or supernova only happens when the mass is sufficiently large. That means that when we say that it is sufficiently large, ang pasabot ana niya class kay ang imong elements nga ma-fuse kay mo sapak gid siya sa iron. Kasi in the case of this one, in the case of medium mass stars, no, dili man siya makaabot og iron. Wala pa siya helium pero siguro helium sunod is carbon, no, carbon, nitrogen, oxygen. O kana siya. Posible na mula pa siya sa helium yun, mula pa siya helium pero di siya kaabot og synthesize og iron sa yang core. It's because kanang dili kay mo na nakadako yang mass. So makita na to later unsay effect sa mass di sa kay ma-realize na to ba na the stellar evolution of isa ka star kay determined primarily by its mass yun. So ang makatudlo sa to unsa yang kapadulngan is kaiyahang mass yun. So ma-realize na to na in the next chapters. Dayon kini pong sa ato ang mga low mass stars kay usually anin nila kay nagakuan lang sila class, naga-fuse lang sila up until helium. So hydrogen, helium dayon. Kuan na dan white dwarf na dayon sila. So dili na sila moagi gyud sa kanang heavier nuclei pa ila ang i-synthesize. Okay, so karon ang atong ikuan, last na to nga discussion on stellar evolution would be on the high mass stars. So kini siya wala siya nabutang diri pero kato ni siyang masses sa star nga greater than 8 solar masses. SM. 8 solar mass meaning 8 times the mass of our sun. So mao ni sila ang mga klase sa stars karon nga moabot gyud sila or in their evolution or maabot gyud sila sa time na mag supernovae sila or nga explosion and this also means lang na na-synthesize niya ang iron. Taman nasapak gid niya taman sa iron kay mao man last na pwede ma-synthesize sa isa ka star. So sa iyang evolution, of course, we start with nebula, stellar nebula, or another term is GMC, giant molecular cloud. If you have a giant molecular cloud, and the same thing with the different evolution sa low mass and medium mass, mao siya protostar nga phase. Then after that is maabot siya main sequence. Again, pag maabot na siya main sequence class, that means this star now is synthesizing hydrogen as a fuel. So mao nang matawag na nato sila as main sequence star. So kung mag-synthesize na siya sugod sa hydrogen and by nuclear fusion, the star will fuse the hydrogen or the proton into helium ions. So our sun right now is currently in the main sequence. So main sequence star na siya because napa siya sa phase na nag-synthesize siya og hydrogen to helium. Okay? So after this one, so nakita nimo no kung giant kayang mass class, dako kay siya mass manggod, ang force of gravity ana niya is very consab. Diba? The force of gravity as we can see in this equation and ipakita natin sa klase ba. Again, ang kung ano na to ang idea lang, ayaw mo ka struggle kayo sa mga equations. This is basically to support our kanang conceptual na tong agisgutan ba kana. So nakita nimo nga ang force of gravity nimo F sub g is directly proportional to the mass of the object. Now in the case of high mass stars, ang force of gravity na mo compress ana sa imo ang stellar nimo nga kuan bitaw class kato imong molecular cloud or stellar cloud nimo is very great sab. So that means nga kusog sab kay or dako kay magnitude nga mo compress ani kay ang force of gravity niya due to its mass dako man sab. So mauna na when the compression is very hard, so syempre mugamay ni siya no. So mugamay ni siya from a very large volume, it will occupy a smaller volume and as a consequence is the heating up of the core. So mag-heat up ang core, mo nang nakita nato na blue siya karon class. So magsugod gid ni siya kining mga giant high mass stars, magsugod sila as blue. So that means they are very hot. Kay di ba ang low mass na to, low mass, nakita na to ang low mass no kay ang iyahang gipadulngan is I mean it started after the protostar, nag main sequence na siya ba? Meaning it started fusing helium, hydrogen to helium, red star siya. Tapos ang intermediate or medium mass stars, so medium mass ang iaasab kay yellow, like our sun. So yellow. Now in the case of high mass HM kay ilaang kuan na ni class kay ano sila, they are starting as a blue star. So with very high. So makita man nimo na sa kuano, makita nimo na sa katong Hertz Sprung Russell, balikan na to later para makita ninyo na ang mga blue stars, those were the stars na init yung kaya siya, high temperature. So tungod na kay dako po yung force of gravity, so pag compress ato nila mas grabe ang heating up sa iyang core na part sa imong star karon. So after that, at 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 a later time no sa iyang evolution. By the way, kung kining mga high mass stars pud ay class kay mausab ni ang fastest nga mag-exhaust sa ilang fuel. So fastest exhaustion of fuel ni sila. Okay, sorry, nagkakuan ako ang kuan. So this is the fastest nga exhaustion sa fuel. So makita nato later marag mahimong sensible sa ato ang paspas sab kay ni sila maggamit sa ilang fuel. Okay? So one example, one explanation is tungod sa ila ang kuan class, tungod sa ilang pagkadako sa mass, dako kayong force of gravity, so dako sab kayong temperature nila diri. Paspas ang pagsaka sa ilang temperature ba, mao nang makasynthesize siya more and more pagyud na mga elements, manang paspas niya mahurot yung fuel kumbaga. So red supergiant na ni siya class. So red supergiant, and then after the red supergiant niya nga phase manggod kay ang mahitabuan ni kay kadumdum mo sa medium mass star, if nakay star ani di ba nako ganina sa medium mass, tapos kini ang yang part sa yang core, the synthesis of heavier nuclei happens on the core. It's because mao lang siya ang naay sufficient nga energy or temperature bitaw nga taas kayo. So pag mahurot na ang hydrogen fuel sa imong core, meaning kung mahurot ng hydrogen fuel, nahimo na to siyang helium nuclei imong core. So ako lang gid yung nahitabo na helium nuclei ang core, pero dili bud pasabot nga nawala na ang hydrogen. Nagyap mo kay hydrogen or proton H11 to be specific, nagyapon ni siya sa imong surface kaso wala sa core. Okay, dayon as gravity contracts this further kay mi shutdown lagi ning imong core ani kay wala na may fuel. So mao ning mo rise ang temperature no, mosakan temperature sa imong core. Tapos dili pa gyapon maka-start og kuan, dili pa gyapon maka-start ni og synthesize na imong nuclear fuse imong helium kay di pa taas kayo, dili pa mao ang temperature niya. Pero some of the hydrogen nimo diri or proton nimo diri a class kanang H11 nimo kay nagkuan na siya, nag-fuse na pud siya kay nakuha naman ang temperature. Dayon pag magsaka pa gyud ayong temperature class, mo fuse na nigsugod ni imong helium. So ang giyon ganina wala na ko gingon asa sa paingon kundi helium 2 kuha na siya, helium to carbon na dayon. So na kay helium 2 carbon. So pag taas na kayo mag-fuse na pud ni siya. So mao na reason kato bitong gikan ka sa diri balik ta ha. Diri from main sequence nga yellow star mahimo siyang red giant. Kato nga process niya nahitabo. Kato bitong nagsugod na siya helium na pud to kuan, helium 2 carbon. So in this case, diri sa red supergiant class, interesting kay ni sila kay sa pakun gyud niya ang tanang elements. Moabot gyud siya og high mass star sa pakun niya tanan from hydrogen moabot gyud siya iron class. Then mao ni siya karon kabalo na ta sa reason no, partly on nganong kuan dili pwede sa helium. So ingon ani ang mahitabo for the case of a high mass star. So kini mao ni akong gipakita ganina, gipasabot ninyo nga example diri nag-fuse ang hydrogen nimo diri class kini. So at a later time, kung gingon ako ang musakang temperature, so helium ang naa diri. So mao katong gianan ako ba nga nakoy hydrogen diri class and ako'y helium na din ang core diri. So kini na dayon ang i-synthesize niya padulong carbon. Now in the case of supermassive nga mga stars, dili lang siya mo stop sa carbon kundi moabot gud siya sa iron class. Lantawa ang core pinaka-core ni abot na siya iron ash. So meaning kung ang layer pa sa imuhang star ana karon, kung imo siyang hunahunaon bitaw as ka ng onion bitaw nga naay mga layers sa skin, ang pinakagawas adto mo lightest na kay hydrogen. sunod helium, sunod carbon, sunod oxygen, neon. Mao ni siya ang mga agian niya class, magnesium, silicon, iron. So mao ni ang process niya sa iyang fusion nga mahitabo. Pero kini siya again, mahitabo lang ni siya basta very massive ang imong star. Kay nga naman, kung massive imong star gani, grabe ang influence sa gravity ana niya class. Meaning kung grabe ang influence sa gravity, murag mahuna-hunaan nimo siya bitaw as grabe ang pagkumot or pagkompress niya. So kung grabe ang pagkumot o compress, mausab na siya ang kagrabe sa pagsaka sa temperature ni mo diri sa imong core. So mao nang paspas ni sila mag-die kumbaga ang mga high massive star kay paspas man ang pagsaka sa temperature ani. So meaning paspas kay ni siya from hydrogen, lukso din siya helium din iyang i-fuse pag human sa helium, carbon. Pero isa ninyo nga manote kay na mga nagi mga bilin gihapon sa kada layer. Kay katulad akong giingon no, pag human example, una ani ako lang klaro kung balik ha kay para maklaro gid bitaw. Unang-una ana kanay imong star kumbaga kay kuan na hydrogen tanan. So sa imong core ang gisynthesize niya kay hydrogen to helium nga nuclei. Okay, dara mao ning nahitabo na process atong star no. Pero kung maabot sa time nga mo shutdown na ang nucleus ani or kanang helium na tanan ba, helium na ni ang iyang outer layer hydrogen. So kung lantawan ni man ni diri class kini bitaw sa high massive stars, niabot siya iron. So meaning ang pinaka-last niya nga na-synthesize iron gyud sa iyang core. Dayon mao day ni mga nangabilin dayon. Niya nga mga elements na iyang naagian. So naay mga shell of elements kumbaga. Okay, so this is very essential to life and very essential pud sa ato ang development sa solar system or sa universe kay pag mahimo abot na magud siya sa iron kay kini pag mag-fuse nag iron it will not release energy. Dili mag-release og energy ang iron crust kung dili mukaon siya sa energy. So kung dili siya mag-release og energy, buot pasabot is wala nay, di ba katong niana ta ganina bitaw nga ang star kay balance na siya sa imong thermonuclear radiation or thermonuclear force nga gikan sa energy sa imong core dira kanang mga fusion sa imong core ug sa force of gravity. Now, this time around since iron naman yung core ani class sa mga high massive stars which will not release energy, kini siya nga force mawala ni siya. Walay outward force kumbaga, wala tong thermonuclear force. Mauna siya nga mo kuan siya, ma-overpower siya sa gravity, manang moingon tag collapse by its own weight or collapse due to gravity. Ang gravity karon mo overpower ani kay wala na may mukuan, wala na ni siya ba kini nga arrow bitaw nga mo counter ana ang thermonuclear force nga gisustain kumbaga sa imong energy sa imong core. Wala naman siya i-release nga energy. Mauna nga ang gravity maoy mo overpower or overrule sa imong massive stars. Karon ang mahitabo kay ngun ani. Okay, the inert iron stops producing energy so but continues to produce neutrinos. Of course, kabalutan na byproduct yun sa fusion tong neutrinos, no? Neutrinos kauban sa katong mga radiation or beta photon. So katong sa atong previous na discussion ba. So kana ayaw mo kakuan sa technicality ha, ang idea lang ba. So kato wala na gani gi-produce ang imuhang energy ang imong core ana nga iron, mag-release na siya continually og neutrino class. Kaya di man na mo interact sa matter ng neutrino, so manggawas na siya diri. Dayon, of course, since that neutrino, energy ra gyapon na siya. So it corresponds to energy. So but pasabot, magpadayon og decrease ang energy sa imong core. Okay, or energy nga gi-release sa imong core. So ang mahitabuan na karon, the density climb, protons and electrons combine to produce neutrons and more neutrinos. So mapugos to imuhang proton ug imong neutron to combine tungod sa grabe nga force sa imong gravity ana karon or mag-release magud siya energy so mapugosab nga wala na ning flux bitaw or kini siya wala na ni as I've said so kung gravity ang overpower. So sudden loss of energy causes the core to collapse from lack of pressure support. So ayaw mo ka wala kining pressure support mao na natong giingon nga thermonuclear force or thermonuclear pressure natong giingon ganina. So tungod kay wala na ni mo collapse din na siya due to gravity. So regions around the core are unsupported. So syempre wala naman ning kining arrow.
So maoning kaning gagmay na araw maoning action sa gravity. Ang gravity na maghari-hari karon kay wala may counter nila. Kay wala na lagi tong core nagahatag og energy. So neutron densities are so high in the core that it is incompressible and rigid. So marag tungod sa density sa imong neutron sa core, sa imong iron no, grabe siya ka dense class such that mura bitaw siya ma-visualize nimo ay the best visualization I could think of is nakay bola, nakay steel bitaw nga ana, tapos nakay bola nga i-throw. So pag i-throw nimo ning bola diri, mo bounce back na siya class mo ani ni kagahi na karon or ka-dense na ang imo ang core sa imong star. So mahitabo ani, so di ba kini makita nimo nakay mga layers karon except from the layer na iron sa core. So kining mga layers of hydrogen, helium, carbon up until silicon tungod sa gravity, i-compress man na sa gravity padulong sa center, padulong sa core. Mangdaga ni silang paspas kay padulong diri. So na sila velocity padulong dira that is brought about by the compression due to gravity or the collapse due to gravity and mo rebound na din sila pag igo nila sa density sa iron core which is very very dense in the case right now ani nga time no pag igo na nila class mo rebound na sila and bringing with them shock wave. So pag rebound na nila shock wave mao nang ma-blast ang surface sa imuang star. And that is what we called now mo na ginatawag na to nga supernova or supernovae or unsa ba. Mao na siya mahitabo karon no. So neutron densities are high in core, that is it is incompressible and rigid. In falling layers, as I've said, strike the core and rebound. So in a fraction of second, imagine in a fraction of second, wave of matter forms a shock front and moves outward towards stellar space. So mag-form na siya og shock front which results to shock waves. So shock waves hit surface of star and explodes. So inward shock compresses remaining stellar core into either a neutron star or a black hole. So after the supernovae, the star would either be a neutron star or a black hole, which we will not discuss right now because that will be for a separate discussion. So, ang rough idea lang yun sa stellar evolution atong gikuha ni class. Kaya ato ang concern ani kay nangutana ra man ta nganong na mga heavier elements. So see nakaabot ta sa iron jud. Then pag moabot na ta sa iron, mao na ni pinaka last nga element nga i-synthesize sa usa ka star. Tapos pag ma-synthesize na ni magkaroon na ta ng type 2 supernova or core explosion supernova. So ingon ani ang makita sa observation sa itong mga astronomers ana class. So nakita nimo ni na picture sa taas ug sa ubos. So kining naay murag kini nga area diri, this is the area of a star na nakita nila sa data na nag-explode in the form of type 2 supernova. So nag-explode na siya and then makita nimo ang significance niya no kung imo i-compare sa previous is its location diri dapit is wala nimo siya nakita ang star gid mismo. In fact, ang makita nimo ang core lang diba sa imong galaxy siga kayo. Pero ang incident sa supernovae, it will result yun class into a star that will outshine the galaxy. Okay, nakita nato diri lang tawag gani kining naay dotted. So nakita nimo before supernovae murag wala siya ga-exist. Pero after supernovae, it outshine the entire galaxy. So, natawa, klarong rin kayang siga. So, they ended up majestically. So, murag they are one of the proof bitaw na not all endings are supposed to be sad. Pero murag kuanat poetic na tani no. Not all ending are supposed to be sad. So some could be an ending na kanang nindot. In the case ingunani nila sa supernovae nga explosion. For example, kini siya, this is a more colorful na example. So kini the Tarantula Nebula and the Supernovae 1987A in the LMC. So, nakita ninyo kini siya. Ang sumao ni atong Tarantula Nebula no. So, lantawa, the nebula was outshined by the Supernova 1987A. So, yun ana ka powerful ang supernova explosion. And nganong importante kay na siya class, it's because the supernovae nga explosion, di ba nakahimo man siya hydrogen to iron. Okay? So mao ni siya ang iyahang mahimo karon nga tawag ani by some processes which we will discuss on probably next week, na some processes ani kay mao na dayon ni ang mag-seed nga makahimo na tag heavier elements. So tungod sa supernova kay energetic man kay to, no, energetic kay to siya nga event, so meaning along with the supernova kay naatay release of energy in the form of photon and radiation. So kana siya neutrons, of course na mga neutrons na mga daghan streams of neutrons nga ma-release. So natay process din karon nga ginatawag na neutron capture. So kining neutron capture, which we will discuss next week, mao ni siyang process nga nag-made possible nga natay mga elements plus iron, meaning elements plus beyond iron nato karon tungod ani nga process nga neutron capture. And it is possible, largely possible in large percentage gyud diri sa supernova nga nahitabo class X supernova nga event. So this is like one way of mura bitaw siya, if you can think of the supernova event as the death of the star, pero actually nahimo siyang seed na pod for another generation of heavier elements. So morning supernova. So syempre ang katong mga elements nimo from hydrogen to iron, mas masabwag na po to, or mas scatter na po to siya sa uban nga deep recesses of space, which probably in the long run mag generate na po siya og kanang mahimo na po siyang star. Depende sa amount of matter nga ma-accumulate niya ato. So kana ang ka-importante niya. So kinahanglan na atay supernova nga explosion nga mahitabo sa atong star para although mamatay ang atong star, but it will become a seed also for heavier elements. So the technical discussion on how we have elements higher than iron will be discussed in detail next time on the neutron capture. So I think that would be all. And if you have any question gonna class, do not hesitate to email me or message me on Messenger if there are things which are unclear to you or you are confused. And just a heads up, I will be posting self-assessment on quizzes. So it's a multiple choice question regarding on the topics that we have discussed. So dito siya recorded class. It's just for you to find whether kana bitawng nasabtan ba ninyo ang mga topics. So makabalo sab mo kung masayop mo nga hala diri gyud ko nga topic wala kay kasabot. So I need to review on this one. So I'm hoping you have fun and you've learned something from this session. So I think that would be all for the day, and enjoy your weekend.